Hello everyone, welcome to this time I'm doing a bit more of a different kind of format of video. Instead of breaking the chapters down into the different concepts, I'm just gonna plop the whole chapter onto one long video with a bunch of practice problems at the end of the video. And this chapter is going to be one of the most difficult chapters so far in Gen Chem, which is an intro to organic chem, so chapter 21. Well, I'm going to get right into it. Try to make this quick so it's not a long video since it's just purely meant to be a summary. So to start off with, our organic compounds are compounds that include carbon, which is important because it forms strong carbon-carbon bonds, and a lot of biomolecules are made of carbon. And now, in organic chemistry, there are two different types of what I say saturations, I guess. So the carbon-carbon bonds or carbon-hydrogen bonds can have one bond, which is unsaturated, and then, which is saturated. I'll move it up here. And then, actually I can't move it, but unsaturated are the ones with double bonds or triple bonds. And later on, as you go down, I add more notes, but usually the only ones that are saturated are out of like the big three, I'd say. The alkanes, alkynes, later on we'll see, but only alkanes saturated, while not only, but they're more, but for now, the most important saturated member is alkanes, while unsaturated include alkenes and alkynes. And I'll get more into this later on as we go on. And then alkanes now. Alkanes, like I said earlier, they're all single bonds. They're saturated. Examples are methane, ethane, and alkanes. The diagnostic feature of alkanes is that they end in anes, like the name alkanes, anes. And then the number, the meth, eth, prop, the number of, what I say, the name is also determined by the number of carbons they have. So methane, one carbon, ethane, two carbons, propane, three carbons, what else? Butane, four carbons, pentane, and then it gets easier from here. It's just root words. Pentane, then hexane, then heptane, then octane. Let me write it 6, 7, oct for 8, octane. Then nanane, something like that. 9, and then decane. 10. It's just, these are skills that I think I've picked up just throughout my life, knowing the root words for like 6, hex, hept, oct, nan, dec, but it's important to remember it. And next thing on the list is the boiling point increases as you add more carbons. So the boiling point of butane is higher than the boiling point of methane because it has more carbons. And now butane are the only ones that exhibit structural isomers. Butane plus. So for this, with methane, obviously we can't have a structural isomer because the methane is it has only one carbon. And remember, a key thing to know about these is that in all these, the carbon has to have 4 bonds, and the chemical formula for it is CN. So let's say N is methane. The N is the number, so methane is 1N, ethane is 2N. So CN, and then H. They all have H's, and the H is determined by 2 times the N plus 2. So you can draw it out to see what they would look like to determine what the H would be, but this is just a general formula that these all follow. It's rare in chemistry to see a formula that everything follows, but methane looks like this, just H, so 4 different H's, because remember, carbons always have to have, carbons equals to 4 bonds. Carbons always, well, I don't know about always, but in organic chem, I'm almost 99% sure it always has 4 bonds. So this is what methane would look like. And if you were to change it to ethane, so 2 carbons now, the 2 carbons have to be bonded to each other. And now for it to have 4 bonds, this carbon can only have 3 hydrogens now. Like before, this carbon had 4 hydrogens, but now one of the bonds is taken up by another carbon, so they can both only have 3 hydrogens. And now the formula is no longer this formula is still this, but then it's no longer CH4 since now we have an X or C, so it would be C2. And then the H, how to determine the amount of hydrogens it'll have is the N, which is 2 times 2 plus 2. So 2 times 2, 4, plus 2, 6. That's the amount of hydrogens it'll have. And she lost track of where I was, but something like that. And oh yeah, I was talking about isomers, structural isomers. For things like this, one more. Let me draw propane as well. Propane would be quite similar, but 3 carbons. And then the edged carbons always have 3 H's because it's only connected to the, like the middle carbons on the other hand, look, it has 2 H's, but then the ones on the outside always has 3 H's because it has to have 4 bonds, and one of the bonds connected here, and then the 3 has to be filled up by H's, while the middle has 2 bonds connected to a carbon, so it only has 2 left, which is then filled by H's. And one thing about it here is the reason why none of these, so methane, ethane, and propane can form isomer. Actually, hold up. Yeah, alkanes can form isomers actually, but not cis-trans isomers, not the geometric isomers, but it can form structural isomers. But these can't. So only butane, lower, and these included as well, can form isomers. And the reason why is because no matter how you flip this, it's always going to look like this. No matter how you flip this as well, it's always going to look like this. No matter how you flip, well, you can't even flip this because it only has 1 carbon. So even if it's always going to look like that. But then when you go over to like butane where it has 4 carbons now, I'm going to draw it 4 carbons. So H, 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 H. And the reason why this can have isomers, like I was saying, is because you can move, since these two here, you have these two, I'm going to pay attention. So usually, generally, you can't edit, or you can't have an isomer of the outer ones, because they always have to have CH3s on the outside, so C and then 3 hydrogens on the outside. But the middle ones, you notice how you can connect this carbon to this carbon, and then so change the middle ones and they look something like this instead. So the outer ones are still here, but then the middle ones are shaped this way instead, where carbon, carbon, and then one of them has 3 H's now, while this one only has 1, because then it's connected to 1, 2, it's connected to the other 2 now, so it still has the 4 bonds. That's one thing to know. And now this is isomer because it changes the what is connected to what. So over here, the H's are now 3 H's are now connected to 1, instead of here where it was just 2 H's connected to 1. 2 H's connected to 1. Now it's 3 H's and 1 H's. So they split. So these two focus on, I'm gonna use a different color now, green. Focus on these green carbons in the middle here. Notice how both of them together, they share 4 H's. But then when you share 4 H's with someone, one of them, they can both either have 2 each, or one has 3 and one has 1. And that's what makes the isomer, because they can form these 2 different kinds of structures. But anyways, you don't have to like know in deep detail, but you have to generally know what a structural isomer is and how alkanes can form it and stuff like that. And now we already did all that, we're here. Isomers allow for different properties. It's also more of a thing to know. There was an article that I've heard the professor shared in class about how in pharmaceutical companies, an isomer of a drug can have different effects. It's just something to keep in the back of your head. A lot of these things are something to keep in the back of your head. And usually because, like, look at this. Also, I forgot to name it. I'm not sure this is important, but in the naming of isomers, so N-butane, it's called N-butane because the N stands for normal butane, while the other one, this, which is an isomer, is called isobutane. I'm not quite sure why it's called isobutane, but one thing that I saw from a random TikTok video is because usually when it's called iso, it means it has identical parts. So that means it has, so if you look at the actual structure, it has this, the CH3. They're like 3 CH3s with 1 carbon connected to all 3 of them, and an H. So that's why it's called isobutane. And another trick to know is their formulas in terms of determining the isomers. So fresh off the bat, we know these 3 have 0, 0, 0 isomers, and then butane has 2. And then the formula to determine the isomers is 2n minus 1, where n is the number of previous isomers. For example, pentane I know has 5 isomers, but how did I determine that? Because the previous one, butane, had 2, and it's 2n minus 1, where n is this, where n is 2, and it's 2 times 2, 4. Pentane has 3, sorry. I realized I did the math wrong. 3. It was hexane that had 5. And then 2 times 2, 4, minus 1 is 3. And then over here, it's the same thing, 2n minus 1, where n is 3. 2 times 3, 6, minus 1 is 5. And then heptane has 2 times 5, 10, minus 1, 9 isomers. And then octane has 2n minus 1, 2 times 9, 18, minus 1, 17 isomers, and so on and so forth. So if you're asked for a test, you don't have to memorize 3, 5, 9, 17, but if you memorize the formula, 2n minus 1, and you know n is the previous isomers, and just remember butane has 2 isomers, n and iso, and you can determine how many isomers the rest of them have. Also remember the formula for how to write alkanes, and later on you're going to see the formula for how to write other things like alkenes, like we earlier talked about. And now next up, where I already touched on this, N-butane and isobutane. And then, like I said, pentane has 3 isomers, and iso again. So the N and the iso remain. This time there's a new one called neo, which is it looks like like the previous like this iso, where it's 1 carbon connected to 4 other carbon groups. That's what neopentane looks like. Anyways, for the naming is gonna stay the same for damn near every other compound. So it's going to be prefix, root, and then suffix, where usually the suffix is the end of the compound you're trying to name. Like for example, alkane, suffix is ane. Almost, or if not all the compounds end in ane, because that's the suffix of the actual compound, ane. And then the root is the number. So for like methane has 1 carbon, so it's meth, and then the suffix ane. And then the prefix is usually also another number, so like where the substituents are attached to, if you have substituents. And substituents is it's a key term. Let me highlight it. Where is it? Substituents. It's a key term, and it just means the things that are attached to the chain. So for example, if we have this is 1, 2, 3, 4 carbons, so this is like butane. But then if we have CH3, which is methane, attached over here, this is a substituent, where the main compound is the longest chain, which is this. 4 is the longest chain, and that's the backbone. That's why it's called butane. But then if it has something attached to the longest chain, then this is a substituent, and you name it according to the number, which is what it means where it said substituents are where attached and the prefix is the number, and then you name it according to the number. So this is and usually the number you use is the lowest number. So for here we can start 1, 2, 3, but we realize that substituents is at 3 versus if we start here 1, 2. The substituent is at 2, so we use 2 instead of 3. And when we do that, it will be butane at the end, obviously, but then it will be a meth in front of. And instead of methane, we use methyl. It ends in IYL if it's a substituent, which is the point here. Ends in YL, like methyl, ethyl, propyl, because it's a substituent. And then you put the number 2 in front, and we just name this compound. Next up, trying to get through this quickly, like I said. The next up is some substituents can be different. So there's like isopropyl, which remember how I told you propane doesn't have a structure isomer, but then when it's a substituent, there are different ways. Like if the propane group is attached to the first carbon, and then it's like a chain, if it's a chain, then it's propyl. But then if it looks like this instead, it's isopropyl. And the reason why is because It's one, like I told you earlier. In this, when we were naming this, we named it was iso because it had identical parts surrounding it. It's the same in propane. If it has CH3 here, identical parts surrounding it, and remember the shape, then it's going to be isopropyl because it has two methanes and one carbon in the middle here. And that's why it's called isopropyl. So you have to remember the substituents do matter. The shape of the substituents and how it's connected do matter. But it will follow the same other rules, when instead of just propyl, it will be isopropyl. And butyl has the same thing, where there's regular butyl. Did I write it down here? Oh yeah, up here. Regular butane, or butane, which is this obviously. And then if it's a substituent, it will be regular butyl. Then there's isobutyl, which is this. It's connected to one. And then there's sec-butyl, which is connected to the carbon that is. So this is the carbon that it's connected. The rest of it, let's say it's attached to a longer chain down here, which is R. R, when you see R in this note, these are my notes by the way, when you see R, it usually means like a longer chain of organic compounds or an organic molecule. So just random thing, like could be heptane down here. And if butane's attached to it, the C that it's attached to, if it's connected to two other C's, which it is here, then it's sec-butyl, secondary, second, two C's, and then tert-butyl, tertiary, three, when the C, the R group attached to the C and is connected to one, two, three other C's, usually methanes. That's the thing about these, it's usually methanes right here. It's attached to one methane and something else. And sorry, I got interrupted right now by my friend Dira. But I think we are done with this part, and then move on to the next part, where alkanes are fairly unreactive. That's another thing to remember right here. Let me highlight it. Fairly unreactive because they are saturated. And the reason why is because carbon-carbon bonds are strong, and it's hard to break apart. And we know that single bonds usually have sigma bonds, which are stronger than pi bonds, which double bonds have. So it's harder to break apart. That makes it less reactive. And they don't react with acid and bases. It's not really as important, but I guess something to keep in the back of your head as well. They react exothermically with oxygen high temperature, which goes into the next topic, which is the reactions for alkanes. Combustion reactions, like this, like it says here, reacts exothermically. So basically, like methane, you've probably heard of it, like a methane gas used for fire. Alkanes can have combustion and then substitution with halogen, where instead of CH4 it becomes CCl4, and Cl is a halogen. So the halogen replaces the hydrogen. And then dehydrogenation, which makes the alkane go from alkane to alkene. And we're gonna get into alkenes pretty soon. But alkenes usually have one less hydrogen, and so like let's say not pretend, this is actually ethane, with two carbons like I showed earlier. This is ethane. If you take out, if you add a double bond, so I'm gonna redraw it here. C, then double bond, C. If you add a double bond to the C over here, like I did here, and remember carbons always make four bonds. If you add a double bond to both of the carbons, that means one of the hydrogens, so this is already 4 bonds. You can't add the last hydrogen. So that means this last hydrogen isn't there anymore, and it loses it, so it can form another bond with the carbon. And that's what dehydrogenation means, basically, where it loses a hydrogen, or two hydrogens, one from each carbon. Each carbon loses a hydrogen, so it can make another bond between each other, and that's what dehydrogenation is. And now cyclic alkanes are just they're just alkanes, so single bonds, but they all connect to each other. Like that's the name suggests, cyclic, so circle. So it goes from this point to this point to this point to this point, but the names remain the same, just cyclo in front. 4 carbons here, butane, just add a cyclo. 5 carbons here, pentane, just add a cyclo. And another one thing with cyclobutanes is that since they connect to each other, so if you remember earlier, the let's do cyclopentane. So not pentane, propane, 3. So cyclopropanes are like this. Oh, I did draw them out here actually. I already drew out here. So remember, they have all carbons have 4 bonds, so connects here, here, 1, 2. They all have 2 hydrogens connected to them. So overall, the formula for a cyclopropane is C3, because propane means 3 carbons, and then H, 6. And regular propane is C3H8, like the formula earlier suggests. The reason why this is regular over here, the reason why it loses 2 hydrogens is because, so this is regular propane, H, 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 and then an H. The reason why it loses the hydrogens is because these 2 carbons at the end connect to each other right here. The 2 carbons, if this was a straight line, so imagine this was missing. There's no extra bond between these 2 carbons. But then in regular propane, there's no bond. So that means that the 4th carbon connection point just goes to a hydrogen, and this one goes to hydrogen as well. So you have 2 extra hydrogens in the regular one. But then when they form another bond, like I was just saying earlier about how when carbons form extra bonds, it loses its hydrogen. In cyclo, it forms an extra bond, so it has to lose, each carbon has to lose hydrogen. So it has 2 less hydrogens, which is why the formula for cycloalkanes is CnH2n instead of +1. You don't have to add that 1 anymore. I mean, not +1, it was +2. But you don't have to add that 2 anymore because it doesn't form the carbon spot for the +2 is already taken up by connecting the last carbon to each other. And now this is naming these compounds. So this compound is called, so overall, how to name the compounds, remember as we said earlier, find the longest carbon chain first. And it's this, so if we do this carbon chain, it's going to be, and one thing I noticed here is, if you look at this compound, the longest carbon chain isn't this, it's actually 1, 2, 3, 4, 5, 6, 7, 8. So if you go like that, starting here, this is the longest carbon chain, 8. But if it's a cyclo, we have to remember that the cyclo is on its own. So we look at the cyclo, which is, it's cyclohexane this time, so 6. So we can't include the outside. These are just substituents since they're connected to this ring, and they don't count in the longest carbon chain. So that's why the base is cyclohexane. And then we look at the substituents now. We can start, I guess, here. It doesn't really, if you start here, it's still going to be 1 and 3. But generally, I just like to start at the top, and I think it's usually correct. So we start at the top, 1, and this is isopropyl, not propyl. First, it has 3 carbons, so we know it's like a propyl or something, propane. But it's iso because remember it has 2 identical, and it's connecting to the middle. If it connected here instead, and this was 2, CH2, then it will be regular propyl. But since it connects in the middle, it's isopropyl. And then at 3 is just the regular methane, so 3-methyl. That's what the name, and the other one, the same thing. The cyclic is butane because it's 4. And then, 1, 2 one has ethyl, the other has propyl. And moving on, this is a question that says a student, this is a complicated question, but it says a student gave a molecule with this name. So I drew out that molecule. So apparently it has pentane, which is 5 in the middle, 1, 2, 3, 4, 5. And then at the 3, so we started here, 1, 2, 3, 4, 5. At the 3, it has a methyl, and then at the 4, actually it started this way, sorry. This way. The 3 has a methyl, at the 4, it has a isopropyl, so I drew it out here. But then this is wrong because it says this is wrong, and the reason why it's wrong is because the pentane, which is 5 carbons, is in the longest chain when you actually count it. The longest chain is 6, so it goes this way. That's why the name is going to be changed to hexane. And then it has, when you make it this is the longest carbon group now. It's connected to 3 methanes, which is 1, 2, and then 3. That's why it's tri. If it has multiple substituents group, you add di of the same, actually, since there are 3 methanes and methanes are all the same. It's tri-methyl. And then you number where they are. This is 2, 3, 4. And we started here, because that's, if we started here, they're giving us higher numbers. So we start where it will give us lower numbers, which is 2, 3, 4. Moving on. Finally, we're in alkenes now. Alkenes are double bonds. They're just like alkanes, the exact same, but they have double bonds instead. Alkynes have triple bonds. And then the naming is also a little bit different, because now you have to number where the triple bond or the double bond is found. And in alkenes with 3 or less, so in methane, actually you can't even have a methane, alkene, methane, because remember, alkene has to have a double bond, and methane doesn't even have another carbon to double bond with, and hydrogen can never ever form a double bond. So you can't even, methane's not a thing at all. That could be a question, which of these don't exist. Methane doesn't exist. And but that means you start with alkenes, so 2 carbons. But then with 2 carbons, you can't really number. So like in the name, I said in the name you number where the double bond is, but if there are only 2 carbons, I'll draw it out here. I already drew it out here. You can't number it because there's no point of numbering it. Like if you number it 1 ethene, it's always going to be 1 ethene. And then in 3, you can't number it either, because let's say if the double bond was here, you're going to have to start at 1, because that's where it started. It's 1 propane. But if the double bond was here, and this wasn't a double bond, it'll also be 1 propane. So it's always going to be 1 propane. That's why you don't number these ones. But then when you move on to 4 carbons, the number actually matters, because if it's here, then this is 1 propane. If it's butane, let me write it down. Butane. If it's here, it's 2 butane. If it's here, it's 3 butane now. Now we move on, and also alkenes can't actually, I didn't mean alkenes, I meant alkanes can't form cis-trans isomers. You just have to remember that alkanes can't form cis-trans isomers, only alkenes can't. Complication, I mean the reason why it's complicated, but it's because they can rotate easily, so they don't have to form isomers because it's easier to rotate them. Whereas double bond, they have restricted rotation. So if this molecule is to rotate, it could form an isomer. Not this one particularly, but it's just important to know only alkenes can form. Alkenes only can form cis-trans isomers, which is also geometric isomers, like I wrote here. And now to name the name these alkenes, remember you find the longest carbon chain, which is like that. You can't, it's not, so you can, I was going to say you could go straight all the way, but you can't really go straight all the way, because if you go straight all the way, it's going to be 5. Whereas if you take this little junction here and go up, it becomes 5, and then you have another one, so 6. So it's hexane. And now if you make it go like that, then you have a methyl group attached here at the 4. Or actually, this is wrong. It's not at the 4, because we're trying to, remember, like I said earlier, trying to find the one with the lowest. You're trying to number it, make the order of the numbers so it gives you the lowest numbers. Oh wait, it is a 4. My bad. It is a 4 because of the double bond. We have to do it in accordance. So I was right about you have to number it with the lowest, but you have to number it with the lowest double bond, and the double bond is at the 2. So if we started the number in here, it would be 1, 2, 3, 4, 5. The double bond will be almost at the end 5, which is way too high. Not way too high, but you can do it another way. That gives you a lower number than a 5. So you have to do it in accordance with the double bond. It doesn't matter. So this numbering it this way would be better for the substituents. But then when there's a double bond or triple bond, or like a functional group, which we'll get to later, it's always important to prioritize those groups first. And then this one is heptane because it has 7 carbon chain, and then it has methyl groups attached to the 5 and the 2. And we number it where the bond over here has the lowest number. So instead of starting here, it will be where it'll be 1, 2, 3, 4, 4. We start here where it'll be 3 instead of 4. Moving on to alkenes reactions. They can have addition reactions. So remember how alkanes can have dehydrogenation, so taking out a hydrogen. Alkenes this time have addition, which is hydrogenation, add in a hydrogen to make it into an alkene. So you can go from alkane. If you go from alkane, so let me write it down here. If you go from alkane to alkene, going from alkane to alkene, you go from alkane, so CH, something like CH3, not CH3 because alkenes can have one C, but like C2H6 to C2H4. To go from here to here, you have to take out hydrogen, so hydrogenation. While to go from alkene to alkane, you have to add hydrogenation from 4 to 6, from 6 to 4. That's one thing to know. And also halogenation is also here, just like in alkanes, where the H's get replaced by halogens. And then polymerization means joining small molecules to form one large one, which we'll get to later. But that's one of the reactions of alkenes. And then this is the question, how many isomers are there in this? I drew them all out, so there are 3. And the reason why is because since it's an alkene, here it has a double bond in alkene, it can form isomers. So that you can swap. This is the first one I drew. It doesn't really have to be the first one, but this is the first one I drew. You can swap this. You can swap the BRs. So here it's cis. You can make the BRs trans, and then you can make it cis again on this side and put both of these at the same side. So the H's are, it's cis to the cis, laterally cis over here, and then not vertically. Wait, if one's lateral, what's the other? The opposite of lateral. I couldn't really think of the opposite of lateral, but I just know like longitudinal, so up versus down. I mean vertical cis, and then there's horizontal cis over here. And now is an introduction to another concept. So earlier we've seen rings, and those are called cyclo. It's like cycloalkane, but you can't have a cycloalkene because instead there's something called aromatic, where it's the alternating of bonds. So over here we can count. Let's count the sides. So let's say 1, 2, 3, 4, 5, 6. So every alternating has a double bond. So 1 has a double bond, 2 doesn't, 3 does, 4 doesn't, 5 does, and though this means it is aromatic. And the most famous aromatic is benzene, and this is another way of drawing aromatic, where they just put a ring around it. And let's say if we have this instead, a cyclic hexane. I mean, we could have a cyclic alkene, but only one of it would have a double bond, so it would just look like this, versus aromatic, where it looks like this, like alternating. That's different from, they're different from each other. And there are different ways of naming aromatic. First, you can name it. So you can name it where the group is, so that if 2 bromines are attached to it, you can name it 1, 2. So the bromine is attached at 1, 2. You can name it according to where the bromines are attached. So 1, 2 dibromo, and then benzene. I told you the base is going to be benzene. Or you can name it with ortho being adjacent, meta being in the middle. What I say? Like here. And then para being opposite of each other. So like this. Like this. These two are adjacent. And for meta I meant the carbon is in the middle. So like here there's a carbon in the middle of both of them. And then if it was here, it would be para opposite. If it was here, it'll also be meta, because there's a carbon in the middle. And That's how you name it. But you can just use the number, and instead of the or OMP, but then it's important to know what the OMP stands for, because it could be asked on a test. And another like keynote or something to keep in the back of your head is with these carbons. So if a carbon has a double, since carbons can only form 4 bonds, if a carbon has a double bond, would I say? If you remember from that's Chem 2C, tetrahedral, octahedral, all that, this is a trigonal planar, since it looks like this, but then if it has a single bond, it becomes tetrahedral. Now it has 4 things attached to. And remember the bond angles for tetrahedral. And also, wait, one more thing before I get to bonding. If it has a triple bond instead, it becomes linear. And remember the bond angles, if it's linear, where it's the triple bond, it's 180 degrees. If it's a double bond, it looks like a triangle, 120 degrees. And then if it's single bond, so it has single bonded to everything, then it has 4 things bonded to, and it's tetrahedral, so it has a bond angle of 109.5. Just something to keep in the back of your head. And now we're done with alkenes. So over here, the 3 big ones, I'd say: alkanes, alkenes, and alkynes. Moving on to other functional groups, and things like these ones aren't as important in this class, but there are organic halides, which is just a organic group. So like if something has CH, so CH, pretend they're H's, I'm not going to draw them, and then it's connected to a random chlorine or something, it becomes an organic halide because it has a halogen connected to an R group, an organic group. And now alcohol is just an organic group. So R, just like I said earlier, R means organic group. So alcohol is just organic groups connected to OH. If you have so let's say something like C, H, 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 and then randomly there's an OH, that's alcohol. Ester is where you just have the CH, so an organic compound, and then you have an O in the middle, and then another organic compound, H. And one thing to know is oxygen always has, not always, but usually has 2 lone pairs in the middle, so it's going to look something like that. And if you see a random oxygen plugged into the middle of into 2 different organic compounds with just CHs, then you know it's an ether. And the next one is, there are 2 similar ones, so ethers and esters. I remember this in a weird way, but also might be a little bit sexist, I'd say. I just remember ester is not sexist. What do you call it? Someone I used to know. Not someone I used to know, but just a random name, a random girl name. I remember it because this is a girl, so it has more. This is, I don't know what ether is, but that's just how I remember it. It's a weird way of remembering it, but my brain works in a weird way at times, and that's how I remember esters. It's different from this, and it's important to know that most likely could be on a test because it's something to catch people off guard with. But next up is the aldehyde. Aldehyde is, so these things over here, if it has a C attached to O like this is known as a carbonyl group. And a lot of things have carbonyl groups like this: aldehydes, ketones, esters, like I was just talking about, and amides. But we don't generally have to know amides. But these have carbonyl groups. And also there's this one over here called carboxylic acid. It technically has a carbonyl group, but then if the carbonyl group is connected to an OH, it becomes a carboxylic acid. But anyways, if a organic compound is connected to a carbonyl group, and then on the other end there's an H, then it's an aldehyde. And aldehydes can also look like this, where it's just H, and then the carbonyl group, and then another H. And this is a special kind of aldehyde called formaldehyde. It's just if it has a carbonyl group attached to H, it's just a random hydrogen, then it's an aldehyde. And if it's not attached to H, so if it's a structure like this, then you have a carbonyl group, and then another structure connected to that carbonyl group, then it's a ketone. And carboxylic acid, like I said, it's similar to alcohol. That's how I remember it, but it has a carbonyl group. Now, just like it's like an alcohol with a carbonyl group. Then ester, like I said, also has a carbonyl group over here. And then the difference, it's different from ketones because it has an extra O here. And another unique thing that I used to remember, which is ketone and which is ester again, I'm still on that girl name thing, is that ester is a girl and ketone down here is on a keto diet. So it lost the O. It's not as big as ester. That's something stupid. For all the people named Esther out there, I apologize, but that's just how I remember it. Esther's big and ketone is not big because it's on a keto diet, so it lost the O. It's exactly the same thing except the extra O here. And then amine's very easy for me to remember because I'm used to seeing amino acids with NH2, and then ammonia, which is also associated with nitrogen. So if I just see NH2, I know it's an amine. And then another thing, another functional group is amides, which is different. It's just an amine with a carbonyl group, and it's kind of easier to remember, and also most likely wouldn't be on the test because it wasn't really touched on a lot. And then phenol is just a ring type thing attached to an OH. That's why it has the name O, because alcohol also has O and is also attached to OH. So that's why it's called phenol. Now moving on. So starting with alcohol, there are different classifications of alcohol. There's a primary, secondary, tertiary. And the difference is primary is one is attached. So the carbon that's attached to the OH is attached to, if it's attached to one R, then I know it's primary. If it's attached to two R's, then I know it's secondary. And if it's attached to three R's, I know it's tertiary. And another key thing to know is primary usually has two H's, secondary has one, and tertiary usually has none. But there's a weird alcohol called methanol, where I wrote it down here, toxic alcohol. It's also an antiseptic. It looks like this. So methane, obviously CH and then OH, and it's drawn like this, where it's C and then the three H's. And then the last carbon bond is connected to the, what's it called? Hydroxyl group. Hydroxyl group. And this carbon, remember how I said if it's connected to the rest of a chain, organic chain, then it's a primary. But over here, this methanol isn't connected to anything else. It's just connected to three H's. And it's not a primary because primaries only have two H's usually. So this is just a weird, unique alcohol on its own. Methanol, it's important to remember because it's different from the rest of them. But that's just one thing. And then this alcohol is, the alcohols, also one thing with naming alcohol is alcohols are named according to where the OH is. If the OH is like at the end, then it's one propanol, but there's no point of adding a one in front of it. It's just a propyl alcohol. And then there's another one where if the OH group is in the middle, so here 1 2 1 2, it's going to be a 2-propanol. And isopropyl, remember isopropyl before is in the middle. So if you cover this up, if you cover the OH up, this is the isopropyl if it's connected to the middle carbons with methane on each side. But it's alcohol, so it's isopropyl alcohol. And alcohols usually have higher boiling points than usual. For example, this is ethanol, has 78 degrees, versus just ethane on its own has such a lower boiling point and melting point as well, I'm guessing. And for alcohols, the more C's, carbons it has, the higher the melting point would be. And the reason why the melting point for alcohol is higher than others is because hydrogen bonding. It has a hydrogen molecular interactions that makes it higher. You know how water also has a higher boiling point because, the hydrogen bonding makes things have higher boiling points. Then important alcohols to remember, ethanol, the ones but the ones people usually drink. And then polyhydroxyl has more than one OH group. If you see more than one OH group, then it's a polyhydroxyl. And then phenol, like we talked about earlier, is just, the ring. AR means aromatic. So an aromatic ring connected to a hydroxyl group, that's a phenol. Over here, these are names for alcohols, like I said over here. You count the longest carbon chain, just as always, and it's butane, 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 and then you replace here. You replace the E with the OL, and it becomes butanol. And you number where the hydroxyl group is found, so the second one. Then B, the hydroxyl group is found at the start or at the end, so you don't have to put a 1 in front of it, but it has a chlorine, so it has to be chloro, and the chlorine. So like just like the double bonds, we number it based off where the hydroxyl group is. So here the hydroxyl group is at the start, so that means we start here at 1, 1, 2, 3. So that means the chloro would be at the third one, and then, you know, so forth and so forth. The same thing for this one. Like I said earlier, carbonyl group, and then the aldehydes have carbonyl groups. Right, let me change the color. Aldehydes have carbonyl groups, and the name ends in al. So it's the exact same name and format, but it usually doesn't have, like this has 2-butanol. Usually with aldehydes, they're usually at the end. Like this would be a long molecule or so, and then this would be the end. So you don't even have to number it. While however, ketones, since there's a molecule, then a molecule, and then this is in the middle, the carbonyl group is in the middle, you usually have to number the ketones. And there are things to remember about aldehydes and ketones is that they're made from oxidizing alcohol. And what oxidation means essentially is just adding an O and taking out an H. And that's what oxidation is. So aldehyde, so if this is oxidized, it adds an extra O in here. So which is why it'll be double bonded instead. And then takes out one of the H's. That's, or I think 2 of the H's. Is it? Could be 2 of the H's. Let me see. Yeah, it takes out 2 of these H's actually. And then remember, primary alcohol is one where only one group is attached to this and it has 2 H's, while secondary alcohol is one where the C is attached to these two other R groups. So this and this is attached to this one carbon, and then you oxidize it, so add an extra bond to the H, and I mean to the O, and then get rid of the H, 2 of them actually, like that. That's why ketones don't have an extra H, because you get rid of the 2 H's. And secondary alcohols usually have 1 H, while primary usually has 2. Like I said, all the way up here, 2 H's, 1 H's. So ketones are secondary alcohol because it gets rid of the H's, while here there's still one more H in aldehydes. And then these are some common ketones and aldehydes. So this is aldehyde because it has an H at the end. So methanol, it ends in ol, ethanol. And then this is a ketone because it has 2 R groups. So it ends in -one. So you just propane, and then you take out the E and change it to O and E at the end. So propanone, pentanone, etc. And then this is a unique one, since this is a benzene attached to an aldehyde, so it's benzaldehyde, I guess. And then this is also a benzene but attached to a ketone. So I guess, I don't know why it's called this, but methylphenyl. Oh, because the methyl group is here, so obviously it's the methyl part. And then phenyl ketone, since it's a ketone, since there's an R group here and then another R group here. And moving on to carboxylic acid, these are weak acids with a carboxyl group. This is a carboxyl group if it has a carbonyl group and then an OH. So this is a carboxyl group. It has a carbonyl group inside and it's attached to an OH. And it's formed by, the textbook says strong oxidation of primary alcohol, but what I think it's aldehyde getting oxidized, basically. And why I'd remember that is because, remember, this is a aldehyde. I mean, not O. O's up here. And R, this is aldehyde. And if you oxidize it, add an extra O in here, and that's a carboxylic group. Carboxylic acid, I mean. And to name carboxylic acids, not to name them actually, or is it? Yeah, to name carboxylic acids. They're a mixture of. I skipped this part. We're not in the name yet, but carboxylic acid is if you mix it or if you add alcohol to it, so you add another OH, it just forms an ester and water. Because hear me out. Let me write it up. RCOOH. If you add an alcohol, so alcohol has OH and then another R. This in the middle over here forms water, H2O and whatnot. And now you have, so let's say you get rid of it. Now you have an ester, because remember esters are, oh, and an extra O, by the way. You're left with an O in the middle, because water, let me explain that real quick before I cancel it out. So over here, water is H2O, so these two H's get used, and then one of the O's also get used while one is left. So I'm going to cancel out again. Only one of the O's is left, and now this is an ester if you get rid of these two. If you remember, this is the, formula or structure of an ester. It's R, carboxylic, and then as an extra O, and then R compared to others. And one thing I skipped on carboxylic acid is just like naming the rest of them, like alcohol. So if the R group here, let's say the R group R becomes CH, or what would it be, CH3, I think. If the R group is just CH3, then this adds 2 carbons now, so it's ethanol, so it'll be ethane. Instead of leaving it ethane, we change the N. For carboxylic acid, we add the root words oic and then acid, so it'll be ethanoic acid. And I'm pretty sure this also has a name. This has a common name of acetic acid, which we used all the time in labs. But I'm pretty sure on a test you can write ethanoic acid and get the points for it. Anyways, we're on esters now. To name esters are probably the hardest of all functional groups to name, because you have to combine 2 different things. So remember, in esters, it's 2 different R's. So this R and this R connected with 1 oxygen in the middle. And to name it, you have to name the 2 different groups that's connected. So you have to name the carboxylic part and the alcoholic part. And you name the alcoholic part by just counting the carbons and then putting a YL at the end. So over here, it's 4. So instead of butane, it'll be butyl, and then name the carboxylic part, which has 1, 2, 3 carbons. So propane, but propanoate. And it's not even propanoic, it's propanoate. No 8 at the end over here, O8 and ill. So this whole compound would be butyl propanoate. Propanoate. And then in amines are easier, has the same following the same classifications as alcohol. If it's connected to 1 R, then it's primary, connected to R secondary, 3 R's tertiary, and it loses the H's. So the same thing with alcohols, 2 H's, 1 H in secondary, and 0 H's in tertiary. And these are examples of it. Methylamine, and the naming is just so it'll be like methyl ethyl. It would be the root plus ill, and it'll be methylamine, ethylamine, trimethylamine, and so on and so forth. And then if it's a benzene connected to a amine at the top, it would be aniline and aniline. I'm not sure why it's named that, but it's what it's named. Then over here, these are just ways of writing out alkanes, because it's single bonds. So CH12 is an alkane. It's 5 is pentane, so pentane. It's a pentane. And then this is the expanded form, writing it all out with all the H's. This is condensed form, just writing the formulas. This is a line where you don't have to include the H's, just where the carbons are. And then this is the whole 3D surface of it. So like this is facing this side, this is facing this side, and so on and so forth. Now moving on to a more of a memorization type part of the chapter. Polymers, chain-like molecules. So it's just a long chain of organic molecule. So this actually could be a polymer, just CH, 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 CH. And there are different kinds of polymers. So thermoset polymers, if you make it, you can't reshape it. It's the same thermoplastic. However, you can heat it up and then remold it. And then something here called cross-linking, which is covalent bonds. And then vulcanization. It was made by someone, I'm not really sure, but it's when you add sulfur to rubber and heat it to get a stronger, more elastic rubber. You just have to like be able to identify these in like a multiple choice type way. I doubt it will be a FRQ. And more types of polymers. Polyethylene, just another thing to remember what it is. The simplest polymers, ethylene polymers. And then like Teflon, actually, it's one of them. And then polymerization, there's addition, monomers fallen. So if you put monomers together, they form polymers. And then condensation, where it's small molecules formed for each extension of polymer chain. And the difference between addition and condensation polymerization is addition usually involves C, so double or triple bonds, and it's a bunch of like double, triple bonds all forming. While condensation, what it means by formed, small molecules formed, is that let's say you add two different, and usually condensation involves functional groups. So like some of the ones that I just mentioned earlier, like for example, you could have an OH and then a carboxylic part, so OH, CO, and then they come together. When they come together, like I mentioned earlier with esters being, what did I mention up here? Yeah, ester is a combination of carboxylic acid and ethanol and a byproduct of water over here. When you combine these two together, let me erase this. You combine these two together and you get a byproduct of water. That's what condensation polymerization is talking about, where it comes together. And the way of remembering is condense, it condenses water. So it makes another small product, and it could be either water or generally HCl. And condensation, remember, it has functioning groups, and it usually makes a byproduct if you combine two of those functioning groups. And usually it's OH. That's just what I'm going to remember, because I know that OH was OH. All my life in chem, OH was OH always gives water. And that's one thing to remember. Condensation, as you connect them, they form small little substance molecules like water. And then homopolymers is when it's the polymer is made of one type of monomer. Let me write one type of monomer, while copolymers is two or more, 2+ types. And then dimer is example of a copolymer where it has two monomers. And then these are natural polymers. Include things like, one thing I always remember, it's a natural polymer for sure, is starch. Has a lot of energy in the CH bonds. So these in the CH and CC and the CH bonds. So hair also, cellulose, which is I think it's found in trees, because I know we can't digest it. So in barks and stuff like that. Then their proteins are also polymers, so fibrous proteins, hair again mentioned, and muscle, cartilage, provide support and strength. And then globular proteins, they transport stuff, and they usually act as worker molecules. I'm pretty sure you can find them on like the cell membrane and stuff. And also, surprisingly, amino acids are polymers, I think. It is surprising, but I guess they are. And usually, like I said, in amines, they have this thing, amine groups, NH2. And it's just important to know there are 20 amino acids in general, I think, everywhere, because all animals use the same 20 amino acids. And then protein polymers by condensation between amino acid chains. Remember, condensation, like I said earlier, it condenses, it brings two functional groups. Like amine is also a functioning group, actually. So if two monomers have amines and they come together, it's a condensation polymerization up here, same thing. And now carbohydrates, this is an easier sort of polymerization, remember, because it's just monosaccharides, disaccharides. Monosaccharides mean one type of monomer. Disaccharides mean two. Polysaccharides is 2 plus, or would I say 3 plus? So anything more than 2. So if it has 3 different monomers, it's polysaccharide. And monomers are basically like things that I think pentos, remember pent 5, hexose 6. An example of a monosaccharide is a simple sugar. I'm pretty sure it's just what makes simple sugars? I think it's just glucose. Glucose is the monomer. So simple sugar is just a bunch of glucose coming together. And then sucrose is a combination of, I think, fructose plus glucose. It's just off the top of my head. And remember, see how it's 2 different monosaccharides that form one compound when they come together. And then polysaccharide is a mix of a bunch of multiple things. And here we see hair again. Not hair, starch again. It's an important polymer to know. It's a polysaccharide. And then finally, there's nucleic acid. There's not a bunch of stuff to say on nucleic acids, but just remember all the nucleic acids, both in DNA and RNA. I didn't add the RNA on here, but it's also on here as well, RNA. And then chirality is coming back in this chapter. It's just to know which ones are chiral. It has to be connected to 4 different things, like it says here, 4 different things. And it's just these 3 in the middle that are chiral, because it's connected to this, OH, H, and another group. Now, here's like a sort of a summary thing for all the functional groups to remember. Remember, alkanes, single bonds. The naming is ane. Alkene, the naming is ene. Alkyne is ine. The halide is just the position where they are, and then the halide name, so like chloro, fluoro, bromo, iodo, and then the rest is usually an alkane, and then whatever alkane is it is, or it could be alkene actually, or whatever the rest of the root is. And alcohol is just the root plus all at the end. And then ethers are a bit more complex. I didn't get into the naming, but it's the smaller chain. So if this is a smaller chain, if this is like 1, 2, 3, 4, if this is 4, however this is 5, then it's the smaller one, oxy, and then the bigger one, ane. So for this example, it'll be 4 carbons. It'll be, I think, butoxy pentane, 5 pentane. And then next, aldehydes. Aldehydes, once again, it's just the number of carbons, and then ends in al, the root, and then the suffix is al, so like methanol, ethanol. And ketones is the same thing, but remember, you have to use a prefix, so number where the carbonyl group is, what carbon is connected to the O, and then you put that in front. So if it's 2, we put it 2 in front, and then say 5 carbon, then it will be pentanone, and so forth. And then moving on to the next one, carboxylic acids, just the number of carbons. And I don't think you don't have to put a prefix, so you don't have to put you don't have to number where the carbonyl group is found, since it's usually always at the end. So it'll just be the number of carbons oic. So if it's like pentane, it'll be pentanoic acid with the acid at the end too. Forgot to add that part. Acid. And then ester is, you have to find the non-carboxylic acid group, or not carboxylic acid, the one without the carbonyl group, and then find the one with the the one without the carbonyl group, and then the one with the carbonyl group, and then you name it. So it'll be this one first, it'll be whatever it is, so like methanol, and then how many C's here, so ethanoate, something like that. And then amine, easy to name, just the substituent, so whatever it's attached to, and amine is usually at the end. If it's not at the end, then you put the number where the amine is found, and then it would be like ethylamine, methylamine, stuff like that. Okay, that wraps it up. And then I was gonna make this in one video, but then I can make another video where I just do all these questions. If you want to watch it, tune into the channel. Make sure you like, subscribe, and if you have any questions, leave them down in the comments or hit me up an email.